Hi, I'm Ralph Block. You can blame me for anything and everything you don't like about G-string. With this lesson, I would like to take some of the mystery out of generalizability theory. When most of us first encountered G-analysis, it was either in the context of heavy mathematical statistics or as a black box where you fed in test data on one side and magical results came out of the other. Although much lab work today is done by fancy machines, lab physicians and technicians still have to be competent in manual white blood cell differential count. That's a skill, therefore, taught and tested in respective training programs. Let us take 30 candidates and let them interpret the same 10 blood films. And for each slide, experts have defined a score that marks the accuracy of the interpretation on a scale from 0 to 100. When all is done, we are left with a list of 300 scores. Now let's do some statistics, as I promised, without mathematics. We draw histograms of 300 raw scores with 10 bins, or 20 bins, or 30 bins, or any number of bins we choose. The overall shape of the histograms stays pretty much the same, and it is close to the so-called normal distribution curve for this data set. Because we have picked a convenient sample of 30 candidates, we cannot expect the experimental distribution to fit the theoretical curve exactly. But the bigger the sample size, the better the fit. Let's look more closely at this normal distribution curve. The curve is plotted against the so-called standard deviation or standard deviation scale, not against the score scale. For this data set, a standard deviation turns out to be equivalent to 12 score points. The original score scale is superimposed at the top of the plot. The overall mean of 300 scores turns out to be 65, which we align with the zero of the standard deviation curve. A normal distribution curve is symmetrical around the zero axis. The area under the curve is normalized to be equal to 1.0. The tails extend to infinity on either side, and the variance is the square of the standard deviation. It's usually called sigma square, the variance. Now imagine a little gremlin with a raffle drum containing an infinite pool of values distributed according to a specific variance represented by the red curve. Each raffle draw provides a discrete value, and the closer this value is to the central axis, the more likely this value appears in the drum. And the further away we are from the center of the distribution, the less likely we will get this value. Neither the histogram of the raw scores showing the spread in the scores, nor a histogram for the mean of each candidate, also showing the spread, nor a box plot comparing each of the candidates in detail, including mean, spread, and outliers, does satisfy the dean. The dean wants to know how much of the variability in candidate scores is due to differences in their abilities rather than due to extraneous sources of variability. She needs reassurance that the results cannot be caused by random errors, which would encourage appeals, but that the results truly reflect the abilities of the test candidates. Let's feed the raw scores together with information on the structure of the test to GString, a G-analysis program. Since I am a slow typist, I have prepared a script to make data entry faster. And we have entered a title for the calculation and added comments. And we had specified the subject of the test, the candidates, with a label C, and candidates are crossed with one other facet, namely the slide with label S, both being crossed, and this is the simplest possible design. And this asterisk on the candidate indicates that the data are structured in such a way that we have one line of slide scores for each candidate. We can now enter the location of the data file, and we can see that the first column of the data file just contains the candidate numbers, and we don't need that for our calculation, so we can skip it. We do have to specify sample sizes, 30 for candidates and 10 for slides. We could theoretically save the control file again, but we won't have to. And now we have the first set of results, namely the variance coefficients. 30 for candidates, a bit over 58 for slides, and also about 58 for the combination of candidates and slides. We had 30 candidates, 10 slides, and 300 residual errors, and each with their corresponding variance coefficient. And the last step gives us the mean value of all the 300 scores, about 65, and the G coefficients, particularly the E rho squared, which we are most interested in, that's 0.84, and I should say that the dean is interested too. We could theoretically also save the results, but again, this being a demonstration, that's not useful. The raw score data have been fed through generalizability analysis software, providing us with the overall mean score of 65 and 3 distributions, one each for candidate ability, slide interpretation difficulty, and residual or random or errors. These are then used to create a G-coefficient devised by Lee Cronbach, an American psychometrician in the 1960s, as an extension of classical test theory dating back to the 1900s. The G-coefficient is a ratio of variances. In this case, the variance due to candidates to the sum of all the appropriately scaled variances. The coefficient can be interpreted as that proportion of all the variances in the observations that is due to true differences between the applicants. So to summarize, G-theory is an analytical tool that decomposes the error in a set of measurements to identify and quantify the contribution of each source. For our data set, the E rho squared G coefficient is 0.84. And that's a pretty good value for a small data set as 30 candidates, and the dean should be quite happy. In other words, we consider each individual raw score consisting of the sum of the sample mean plus 3 components, one each for candidate, slide, and residual errors drawn from the appropriate distributions. As a result, whenever a candidate's ability is higher or the slide is easier to interpret, the score goes up. Conversely, when a candidate is less able or the slide is more complex, the score goes down. Usually, G-analysis programs take the scores and extract mean and variance coefficients such that the given data set always leads to the same results. One additional feature of G-string 6 over previous versions is that it allows you to go the opposite direction and construct synthetic data sets from mean and variance components. But each time we run the simulation, even with the same parameters, we get a different data set. Now I have to confess my dirty secret. There really were no 30 lab students. There were no 10 white blood cell slides, and there was no dean. I made them all up to decorate a synthetic data set based on realistic assumptions. However, such synthetic data sets can be extremely useful both for practicing G-analysis and for experimenting with G-analysis in order to gain a better understanding. Thank you for your attention.